So, welcome everybody to the final portion of the 2024 SciVis Contest. Tim Garrett and I were the co-chairs for the 2024 contest. Um, uh, Today's schedule, we're going to start with a presentation of the data and challenges, which I will be doing. And then we have three possible presentations from the submissions. And then we will do the awards. And then we're actually going to have two kickoffs for both the SciVis Contest 2025 and the SciVis Contest 2026. So that's today's schedule. The SciVis Contest is a yearly contest that has been part of the IEEE Viz since 2004. The purpose is to encourage exploration of new approaches to visualize and analyze complex, large, challenging scientific data. And to provide an opportunity for people to work with data sets that maybe aren't always readily available. All right, so the first part is going to be me on presenting the data and the challenge. Slide decks. All right. So the SciVis 2024 contest was focused on imaging deep sea hydrothermal plumes with the cabled observatory and imaging sonar COBAs. So just to give a little context that provides some meaning to the data, the deep sea hydrothermal plumes are found at all mid-oceanic ridges spreading centers, and for that matter, all underwater volcanoes where you have groundwater flow driven by volcanic heat. So these are fundamental parts of a magmatic system. And what we're observing is the outflow of heated groundwater. And because the ocean is cold, that water generally rises immediately. And so I provided a few images, and then here's a video looking at the close-up right where the water is exiting. And this video captures the bottom meter to maybe 2 or 3 meters for a couple of the more distant vents of rise. But the acoustic imaging that I'm going to show us is actually going to capture about 20 or 30 meters above the vents. So it gives a broader view. And in that broader view, we can start to see the connections between the sulfide chimneys and the larger scale hydrothermal plumes. We can see forking and merging. We can see collapsing, potentially collapsing plumes. And we can also see very vertical plumes. So the broad scientific objectives of my work has been looking at heat transport, understanding plume structure, seeing if we can capture chimney growth, and understanding the interactions with the ocean. So COVIS, the Cabled Observatory Vent Imaging Sonar, is the sensor that was collecting the data that was part of the contest. This is a multi-beam sonar that can operate in either 200 kilohertz, which we use for the diffuse flow, and 400 kilohertz, which we use for the plume imaging. That sonar head or those sonar heads are mounted with the receiver, all of that being mounted on a rotation system that has pitch, roll, and yaw. And we particularly use the pitch to be able to move that plane of the multi-beam that's imaging and move that up and down so that we can sweep through space and capture 3D images. In a broad sense, COVIS is capable of imaging modes, which includes both the backscatter volume as well as a potential for setting things up to collect Doppler velocities, although that was only very successful in the first deployment. We also can use the imaging mode to collect similar data to the diffuse mode, so that seafloor. The diffuse mode is, instead of the narrow beam of the imaging mode, it's a wide beam and it's oriented at the seafloor. And the diffuse mode variable is the seafloor backscatter pressure. There were 2 deployments, 2010 to 2015 at Grotto Vent and the Endeavor Ridge, and the data is publicly available through Ocean Networks Canada. This contest focused primarily on, but not exclusively on, the 2018-2023 deployment at Ashes Vent Axial Seamount, which is off the coast of Oregon, Washington State. That's through the US's Ocean Observatories Initiative's Regional Cable Array, and it has its own sort of site. And we were taking the imaging was done hourly, but the imaging mode was only operated 1 day a week, where the diffuse mode was operated the other 6 days a week. So this gives you an idea of where axial seamount is off the coast of the western United States. Ashes Vent Field is on the western side of the caldera, and there's a fiber optic cable that was bringing power out to the instrument and then bringing data back to shore. So when it was operating, we actually had real-time shore-to-instrument communications. So here's a glimpse of some of the data. Looking at the imaging mode data, you can see the time series of the plumes, where I'm showing sort of the different intensities in the red, purple, blue colors, as well as the bathymetry in the sort of green to brown beneath, so that these plumes are coming primarily from the top of the mount. I also tried to use the data to look at chimneys, and the data was provided both in a raw unprocessed form, which is much larger per file, or processed grids, which are about 20 megabytes a piece. As I said, it was collected hourly 1 day per week between roughly 2020 and 2023. The main challenge, so there's two big challenges of working with the data. One of the challenges was extracting the plumes in their center line, and you can see a static image of a plume and my corresponding attempts to find center line points and connect those. And then the other challenge is the gridding process. This kind of gives a little bit of an idea of the height of Cobus relative to the height of the mound and sort of where the pings are going. The data comes in as a plane of beams. So the multi-beam means it's doing beams along a plane, but then each plane is at a different elevation. So the data comes in with this complicated, not rectilinear structure. The process data has been gridded using a Nader's neighbor interpolation onto a uniform grid, because that's the only way the investigators could work with the data to visualize. So the tasks and challenges for visualization were to extract and visualize the plumes effectively to showcase the changes in bending and structure, to extract plume center lines or otherwise quantify plume characteristics such as bending direction and degree, backscatter intensity gradients, and heat flux. And then a third challenge was to see if anybody wanted to think about a more sophisticated gridding or plume extraction that starts from the raw data rather than the gridded data. All right, so let me go back to the main what slide just put on? Main presentation. So I went through the tasks. We had 3 completed submissions, and we did not track the download specific to this contest. Both data sites are completely open and discoverable to the general public. So this data is available for anyone who wants to work with it, even outside of the Viz contest. So our first talk today from the submissions is going to be presented by Yiming Shao and Qian Zeng. PlumeViz interactive exploration for multifaceted features of hydrothermal plumes in sonar images. And with that, I will stop sharing.
Okay. Good morning, everyone. I'm Yiming Shao from Shandong University, China. It's a great honor for me to present our work on behalf of my team. My presentation title is PlumeViz, Interactive Exploration for Multi-Facet Features of Hydrothermal Plumes in Sonar Images. Hydrothermal plumes are a mixture of seawater and hydrothermal fluids, which are generated by the circulation of seawater through the oceanic crust. They serve as essential markers for researchers studying deep-sea hydrothermal systems. In recent years, acoustic imaging techniques have been developed to detect hydrothermal discharges, including plume imaging, plume Doppler velocity, and diffuse flow. Visualization techniques play a crucial role in facilitating the analysis of this multi-source and multi-faceted data. However, visualizing acoustic data from plumes presents several challenges. One major issue is the significant noise in plume data, which is difficult to eliminate. Additionally, the long intervals between data frames make it hard to observe changes in the plume over time. To address these challenges, we have developed an interactive exploration tool, PlumeViz, for visualizing hydrothermal plumes in sonar images. This figure illustrates the framework of PlumeViz. We use sonar data that has been preliminarily processed and interpolated into a uniform grid. Then, in the data pre-processing phase, we convert the data into a readable format and perform some pre-calculations for efficient visualization. In the visualization phase, we provide an interactive method to locate the plume regions and allows users to explore the plume features. Here shows an overview of PlumeViz. At the center of the screen is an area to display the plume. In this figure, our tool showcases an overview of multifaceted plume features. These include a 3D plume structure, centerline, and backscattering intensity gradients, in addition to seafloor topography and diffuse flow patterns. In the lower left corner, there is a minimap where users can click icons to select the region of interest. Additionally, users can modify parameters in the right area to adjust the visualization results. At the center of the screen is a plume visualization area, which displays the multi-facet plume visualizations according to user interactions. We have also provided a dynamic sequence control panel to facilitate the observation of plume changes over time. To visualize plumes and their features, the first step is to isolate the plumes from the background. Our approach integrates automatic data filtering methods with user interactions to address the challenges posed by data noise. Specifically, we first apply an extended region growing algorithm to segment the data into multiple independent regions, allowing us to track the same plume across different timestamps. We then automatically identify the regions containing a certain number of voxels as candidate plumes. Finally, users can freely select and display the regions of interest. To display both the internal and contour structures of plumes, we combine the direct volume rendering with isosurface extraction for visualization. To address the issue of long time intervals between plume data points, we apply linear interpolation to create smooth transitions between consecutive timestamps, resulting in a more continuous data evolution. Plume features such as centerline and heat flux provide insights for domain experts to better understand plume's behavior. So our second aim is to extract multifaceted plume features, such as plume centerline, backscattering intensity gradients, plume velocity, and heat flux. First, we extract the plume centerline. Specifically, we identify the line connecting points of maximum concentration within each plume cross-section along the z-axis. These connecting points are then fitted with a smooth quadratic polynomial function. After this operation, we obtain a smooth curve representing the centerline of the plume. To analyze the plume intensity and direction changes, we calculated backscattering intensity gradients using central differences. These gradients can be visualized as either small arrows or as streamlines. To address the need for research on plume dynamic and energy, we require a comprehensive analysis and visualization of Doppler data. The Doppler data contains the line offset velocity of the plume. After performing some geometric calculations, we can derive the plume velocity from the Doppler data. Then, we draw the streamline using the first-order range-Coulomb method. Heat flux is an important factor in studying dynamic hydrothermal discharges in vertical directions. After obtaining the plume velocity, we can calculate the plume heat flux. Then, we use the classic recasing method to render the calculated heat flux with a rainbow color map and a log-scale opacity function. Given the extensive range of plume imaging data and noise present in extracted plume regions, we offer both region grouping and selection tools to facilitate user exploration. The grouping tool enables users to define the area of interest by adjusting the axis letters with the 3D group displayed dynamically. For more focused analysis, the region selection tool allows users to pinpoint specific plume regions by clicking on corresponding areas within a 2D minimap. Our tool integrates a diverse range of continuous color maps from Python's Matplotlib library. Users can choose their preferred color maps, and our tool will automatically adjust the color distribution to align with the data distribution. Additionally, users have the flexibility to modify the opacity function to enhance the visualization of the inner plume structures of interest. We also provide interfaces that allow users to specify values of extracting isosurface from the 3D plume imaging data. In conclusion, we introduced a novel interactive exploration tool, PlumeViz, for visualizing dynamic hydrothermal plumes in sonar imaging. Our results effectively demonstrate plume bending, structure, and temporal changes. Equipped with interactive explorations, our tool provides an interactive method for plume visualization and empowers users to investigate diverse plume changes. A diverse plume feature. More details about our tool and the source code can be found on this website. Thank you for your attention.
Thank you. Thank you for a great talk. So let's see if there's any questions up on the Slido already. Doesn't seem to be. So when you were doing the backscattering gradients, how did you sort of control the length of the streamlines? I mean, was there a natural stopping place in the data, or
You mean how to calculate the gradient?
well, it looked like the little arrows took up more space than the streamline, so I was just sort of wondering, did the streamlines go to a certain place and stop? Were they stopping at like a certain value, or just where there wasn't any, or the edge of the plume?
Um, uh, Yiming, can you explain how to calculate a streamline with a gradient?
You're muted, I think.
Okay, we found the set points of the streamline along the center line. So we get that.
Okay. Thank you. Let's see. Do we have any questions? Um, we have an anonymous question that asks, can the user record a video of their interaction with the plume data?
You mean the record?
I think what they mean is that if I, as a user, were going to open up PlumeViz and start playing around, could I record a video of my interaction?
Mm, no, we cannot track the interaction. And currently, we didn't provide such a tool uh, to to record the sequences, but you can play it on the fly. Yeah, and it is easy to uh, to integrate such a function. But now the system did not provide this functionality. Yeah.
All right. All right. I guess
Yeah,
since there's no,
it's possible to integrate it in future work if necessary. Yeah.
that sounds like a cool thing. Um,
Thank you.
and I must congratulate you. I am really, really impressed with um all of the work and the very successful visualizations. I love the
Thank you. Thank you.
backscattering gradient streamlines and the view that gives of the plume.
Yeah, yeah.
All right, so I think it's time for our next presentation.
Okay. Thank you for
Briefly,
your question.
let me see. Don't think so. So let's just do that. So our next submission, the second submission, was visualization of sonar imaging for hydrothermal systems by Nigan, Nguyen, and others. I don't believe that anyone is present to present that. Is that correct? All right. So we'll just go on to the third submission, which was by Adhitya, Kamakshidasan, and Harikrishnan, Pattathil, topology-based visualizations of hydrothermal plumes. And I think Harikrishnan is presenting.
Yes. Let me just bring up my screen. you guys able to see it?
Yes.
Yep. Yeah. So, hi, I'm Harikrishnan, and I'm a researcher at Shell. So, me, along with my colleague Adhitya, found the topic interesting, and we decided to work on it. And so here goes. So, this is our topic: topology-based visualization of plumes, which was submitted to the SciVis Contest of 2024. So, this is just a cautionary note from the company point of view. Yes. So, let's talk about the hydrothermal plumes. So these are like underwater volcanoes which are like extremely hot, and mineral-rich water shoots up from the cracks in the sea floor. On the left, you can see a black smoker, which is a type of a vent that releases really hot, dark colored fluids. And on the right hand side, there's a bit of science of how this works, which basically full of metals and like iron and zinc mixes with the much colder seawater at the ocean floor. And that's where things get interesting. So there are these chemical reactions that causes the minerals to clump up together and form the thick, dark smoke which you're seeing on the plume. And the temperatures can get really high, like up to 400 degrees Celsius at the vents. So why it is interesting to us and to Shell in specific? Now what you see here is from the Deepwater Horizon incident. It's a very infamous incident. So this is like an artificial hydrocarbon plume and not a hydrothermal one, like what we saw in the recent videos and the main point of this contest. But the point to note here is there are important parallels between the two. So both of them involve release of fluids into the ocean, and both of them have complex interactions with their surroundings. Now, by studying these natural hydrothermal plumes, we can gain insights into how these fluids behave in the deep sea, which help us improve our ability to monitor and respond to situations like this. Now, at Shell, from a health, safety, security, and environment (HSSE) perspective, which is very core to how we work and how we deliver things, it is very important that we learn from these natural systems to better predict and mitigate the risks uh, in our offshore operations in various parts of the world. Now, with that context, so this is everybody knows about how COVIS is deployed, and so now what we want to highlight here is we have focused main on the backscatter intensity, which develops us to the 3D images of these hydrothermal plumes. Now, so the COVIS deployment, which we saw in the previous slide, gave us tons of data. But how do we start to analyze it? So what we did is by understanding the calendar heat map, sort of like the timeline distribution of this whole deployment, right? So if you see on the figure here, the darker the plot gets, which means the more number of hours the data is collected for that day. And you can see that from July 2019 to November, it was like a kind of a steady phase. And then from December 2019 till March and April side of things, we have data collected every 24 hours on Sundays. So that is what we understood from this deployment. Now, how we did the data pre-processing. When we looked at the raw data, we noticed like a significant amount of noise and some smaller plumes. Hence, we decided to cleanse first. And we did this using a simple connectivity algorithm amongst voxels, which includes individual voxel elements which are connected on a 3D grid or space. And then we successfully eliminated the noise as you see here. So all the visualizations I show are from ParaView, the open source software. How we extracted the plumes. So this is sort of like a time series of the entire dataset. After applying the connectivity algorithm for all the raw datasets, we have 3,645 grids ranging from 2018 July to June 2020. And the one which I showed is like the time series of that data. So we got the plumes now. Now, what are the characteristics of these plumes? Now, while looking at the ISO surfaces of these plumes, we notice a similar phenomenon. The plume should start off with a strong base at the bottom, then have a trunk in the middle, try to stabilize for a bit like here, and then finally disperse into small spores at the top, the yellow ones. Now, these four stages which we talked about are represented here. And you can see that when it starts off the base at the base, and then there's like a region of a trunk, it kind of stabilizes, and then it dies down very fast in the yellow color spores. Now, as we looked at these isosurface distributions, what we expected was like a Gaussian or unimodal distribution, but it had like a bimodal one when we saw it for all the plumes. So we can see that they have like a maxima, a minima, and then a small dip like in between. So now we, using the data which we gathered, we theoretically claim that the bimodal plume can be broken down into three parts: the base, the trunk, and the spore. So the base is between the first minima and the first maxima, the trunk between the first maxima and last maxima, and the spores is between the last maxima and the last minima, where like it dies down very fast. Now, why it is helpful is because we can characterize these plumes according to these. And then based on our observation for isosurfaces, it would make sense in utilizing a merge tree algorithm. So there are two advantages for this. First one is it will give us the structure of the plume. And second one, it will provide the segmentation also. So let's try to understand this using an example. So this is kind of unrelated, but it is just for the example's sake. Let's say we have this armadillo toy here, and then we can define a height field on it. Now the points where it's near the feet, they have the low ISO value, and then they gradually increase till the ears. So the height is the field is increasing. And now when we look at the level sets or contours, the contours start near the feet, join, and then split. So you can see it's going like this. Then they join, and then they split. So these are the facts which we use to understand the merge trees. And the points where the contours start, join, split, and vanish, they're called critical points. So this abstraction which captures all these contours is called the joint tree. And similarly, an abstraction which captures the contour split is called a split tree. When combined, they form the merge tree, which we utilize in our plume analysis. So using the arcs of this merge tree, we can segment any object. So as you see in this figure here, we are able to segment the leg, the torso, using this merge tree. Now, how it is applicable for the plumes? You can see in this figure here, for September 7, 2019, this plume has been captured just between like 1 hour, and it's spread. The plumes are widely different. So how we can utilize this merge tree here? So we can see that the first picture here has very few structures, and the second one is we are able to extract multiple structures using the merge tree. Now, how different are they? So the way to compare these two plumes using merge trees is by merge tree edit distance, which essentially mathematically it means how many changes we have to make from getting to A to B. But here, what it means is how different these two plumes are. And to do that, we plotted the merge trees for all 2018 plumes and compare their edit distances. So what we get is two clusters from this analysis. And the first cluster is of size 145, and the second is of 132. Now, what are the plumes in these clusters? These clusters, which are extracted using the merge tree algorithm, you can see the first cluster here, the very small plumes with less features. And the second plume cluster has very large plumes with high bending and more features. The other use of the merge tree algorithm, the first one which I already told you, is about the structure. The next one is about segmentation. So sometimes we would want to focus on the main plume and rather not go into the branches. So that is where the segmentation comes into play. And it's a central part of our center line algorithm also. So we find the center line using all these. And you can see in the first picture, there is a deviation because of some protrusion. Hence, using a segmentation algorithm, we are able to remove that. And then we are able to get a more structured center line. And we can also use the isosurface plot to remove the spore part, the top part which ends very fast, to get a shorter, concise center line. Now the plume dispersions. From all these, we get the center lines, the bending angles and directions. You can see that in the days where there are stable ocean currents, the plume tends to bend in a certain direction of within 30 degrees or so. And then in some other times or some other days, which is the most case, like mostly this currents in under ocean are unstable. And you can see that the plumes are very haphazard in nature. There is a lot of turbulence in the second case. Again, further analysis, what we find is we extracted some attributes from the plumes, like basic attributes like height, area, volume, hypervolume, average backscattering intensity, the bending angle, which I talked about, the bending direction. And then we performed the correlation plot. From that, we found out that the height, average intensity as in the magnitude of the backscatter, the average one, the bending angle were the most prominent features. And then we performed some clustering algorithms on them, and we plotted them in a 3D space. You can see that it forms 3 clusters. And based on these clusters, what we found out was there were 3 of them. And the first cluster, as you see, the purple one, they had tall plumes which have minimal bending. This may attribute to like lesser or lesser ocean currents with strong plumes. And the second ones, they had very minimal bending, but very high intensity also of the backscatter. And the third one, they had a mediumish height, but what they showcased was they have a very high bending, which could be owed to ocean currents. Yeah, so finally, in summary, we loved working with hydrothermal plumes by starting off with understanding of the data, extracting plumes and the key features. We were able to analyze and visualize the natural phenomenon occurring in deep waters, which could be useful for our ventures as well. So we hope you enjoyed our work. Thanks.
Thanks for a great talk. Let's see. Yeah. So while I'm checking to see if there's any talks online, check questions online. I had a question, and that is, when you were computing the plume distribution curves, were you only using the voxels within the plume?
Yeah, so they were the voxels which we considered after the initial sort of filtering for after using the connectivity algorithm. So basically the main plume is what we consider.
Okay. Yeah, it was just I hadn't picked up on that when I initially read the paper, so was curious about that. And really, really interesting the analysis to get the merge trees and use the merge trees to see the structure. And and that I was sort of wondering, uh, do you plan to publish this work anywhere or? um,
Yeah, we were initially having talks about that. That depends on what the domain scientists would want, and like ideally, we would like to work with some domain scientists to understand what they pinpoint out what they actually want, and then work on it.
Oh, that'd be really cool. You're definitely welcome to email me and my collaborators, and we can set that up. There is
Sure.
one question on Slido, and that is, how do you validate your results? Did you have any access to ground truth information?
Validate to what results?
Yeah, I mean, they said, did you, like, the full question said, do you have access to any ground truth information, maybe given manually by expert, for example, for the access to the plume? My guess is no, but
No, we don't have any access to ground truth.
definitely one of the challenges working with this kind of data.
Yeah.
All right. Well, thank you very much for a great talk, and I will be in touch with both sets of people, but I guess it's come to the time for the great reveal of the awards. And share my screen. So in this contest, we typically give a series of prizes. This time we're going to give two prizes. One is the best paper, for which the winner will be invited to a journal submission at CGNA, Computer Graphics, and I don't know what the A stands for. It's bad of me. And also then we're also going to give an award for the most innovative work. So all the works are reviewed by 6 jury members, which were a combination of domain scientists and visualization experts. And we discussed together the final rankings. So the jury consists of Teresa Marie Rainey, who's an editor with computer graphics and applications. That's what the A stands for. Myself, my colleague Wang Shu at the Applied Physics Lab. So both Wang Yu and I are part of the team that deployed COVIS and has been working with the data. Then we had Delwayne Bonensteel, who's a geophysicist at North Carolina State University, very familiar with hydrothermal plumes. Christian D. Mostier of 10dBx LLC, who had worked with our acoustic data many years ago, so he's familiar with the acoustics and how COVIS as an instrument works. And then Tim Garretts was my co-chair for the SciVis Contest. So first I'm going to announce the most innovative work. We wanted to commend the work with contour evolution and merge trees to segment and cluster plume structures, demonstrating the potential to capture the plume shape, find the center line, and really offer significant insight into plume dynamics. And I have to add that this is exactly something I was trying to do myself and completely failing at. And I am so impressed and so excited to see what you guys did. So this goes to Adhitya and Harikrishnan for the topology-based visualization of hydrothermal plumes. So congratulations.
Thank you. Thank you.
So then the best paper was given because it demonstrated really strong novelty and impressive visualization techniques for analyzing the plumes, as well as creating a complete interactive tool called PlumeViz. They used 4 different visualization methods. They covered like all the different characteristics and types of data. The innovative streamlines of the backscatter gradients also revealed some promising insights into plume structure and dynamics. And we wanted to commend the flexible and interactive visualization capacity. So this goes to Yiming Shao and his team for PlumeViz. And we are just really impressed and excited by this visualization tool. So congratulations.
Thank you, Karen. Thank you. Thank you for this recognition.
Teresa will probably be in touch with you about the potential to do, the invitation for the computer graphics and applications paper.
Great. Thanks.
You're welcome. All right. So thank you for all of the submitters for their interest, effort, and results, for everyone who even considered but didn't actually submit. Wang, myself, and our collaborators are really grateful. This has been really a useful and enlightening process. I also want to give a real shout out to Tim Garretts, who did all the logistics and tracking work. This could not have happened without his stupendous efforts. And then before we leave, we have 2 more presentations, because we're actually going to open the SciVis 2025 and the SciVis 2026 contests. So the SciVis 2025 contest, I'm actually going to be showing a video from Tim Garretts. Yes.
Karen, we can't hear the audio.
Okay. All right. Let me figure out how to do that then. Oh, we have to stop the
when
share.
when you start the screen share in Zoom, you have to click on a button that says share audio as well.
Yeah, so let me work on that. There it is. Share sound. Okay. Back to the beginning.
Hello everyone, my name is Tim Garretts and I'm very happy to share some information on the 2025 SciVis Contest, which effectively starts right now. First of all, I'm sorry that neither my co-chair Christoph Heinzel nor I can present this live, as I'm currently in a parallel session here at Viz, but I'm sure that Karen did a great job getting you through this year's SciVis Contest, which brings me to the first point. First of all, congratulations to the winners, and thanks a lot, Karen, for being SciVis Contest Chair this year and hosting this year's contest session. I'm sure you did a great job and you were a great help throughout the whole year. All right. So with this, let's change the contest's theme. This year, we're doing things a little bit different and move away from the typical SciVis spatial data. We go into the field of material science and look into the visualization-based discovery of novel materials in recycling. So that's what the 2025 contest is going to be all about. So let me tell you a little bit about the background. A lot of industries produce a lot of waste. So for example, old planes have a lot of scrap parts, or pistons are used in cars that can't be used again, which are often made of aluminium silicon alloys. But those materials, those alloys, are still quite valuable and should be reused and recycled. However, when such materials are recycled and mixed back together, the materials can vary greatly based on the mixing ratios of the parts. But in this lies great potential. So we can discover new materials with useful properties, for example, in the aerospace and automotive industries. And the German Aerospace Center has developed a simulation code that tests different mixing configurations of such aluminium silicon alloys and the resulting material properties, and has decided to provide us with more than 100,000 combinations with more than 60 simulated properties. However, as you can imagine, there's a whole space of possible mixing combinations, and comparing all of these properties by looking through a table is basically unfeasible. And the researchers have already looked into some standard visualizations such as parallel coordinate plots or 2D visualizations of subsets, but now we are looking for novel interactive tools to allow to find potential new alloys with desirable properties in this massive data set, and also understand the sensitivities of the simulation. So that's what this year's challenge is going to be about. Right? So finding optimal and robust solutions in multidimensional data and optimization steering. That's the two big challenges. So concerning the schedule, we'll keep things similar as in previous years, which means there's going to be a deadline at the end of July next year. So it's a lot of time for you to come up with some novel visualization approaches. About the data, which is always the thing, the data is almost ready. It should be available to all of you within a couple of weeks. The website is already live and provides you with all the information you need for now. And there's also already a description of how the data is going to be looking like. The data will follow in a couple of weeks. And there's going to be new videos and things like that to support you in the process of understanding the data. We have already, as always, set up a Google group to answer questions or provide you with updates. So it's definitely worth joining it to get all the recent stuff. Or if you have questions, you can directly send us an email to sciviscontest@ieeevis.org. And with this, I would say this is all for now. Please come join us for the next SciVis Contest in 2025, and I'm excited to see what you come up with, and I hope to really see you in person in Vienna 2025. All right, thank you.
All right. So, to switch back. All right, so that is the SciVis 2025 contest. And we also have the 2026 contest. And we have, I believe, both Valerio Pascucci and Amy Gooch here to present that. So let me stop sharing and allow them to do that.
All right. Good morning. My name is Amy Gooch. I'm from Bayshore, and I am here to kick off the 2026 SciVis Contest, Visualizing the Future of Climate Science, one dataset at a time. We would first like to acknowledge our partners in this venture. So we partnered with the NSDF and Wired Global Center, and they are helping to provide the cyber infrastructure. NASA Ames Research Center and JPL provide the climate data and the scientific support. And we have free storage with redundancy from SEAL, OSDF, Pelican, and UCSD. Bayshore itself is going to be putting up $1,000 cash prize to go with this contest. So a big step there. We're hoping to encourage a lot of hands-on with this data. And we would like to thank the NSF and the DOE for the awards that support this project. So we have spent a lot of time already talking about the SciVis contest, so I'll kind of skip to the specific thing. For the 2026 theme, we're talking about visualization of petascale climate data that's freely available from NASA, addressing critical topics like climate change, ocean dynamics, and extreme weather events. And this is partially based on the LDAV paper that was presented yesterday, web-based visualization and analytics of petascale data, equity as the tide that lifts all the boats. And this won the IEEE LDAV Best Paper Award this year. So the focus of the 2026 challenge revolves around 3 data sets. One of them is an ocean atmospheric model, one is ocean circulation, and the other one is downscaled climate projections. And I'm going to go through each of these in turn. The challenge is with dealing with this large data is the fact that it is truly very large, so petascale. We also want to focus on making access to this data interactive and user-driven to enable exploration and address the visual complexities of climate simulations. This is one of the motivating challenges for this. What's kind of started our interaction is working with Nina McCurdy at NASA Ames. And this data set is about exploring ocean-atmosphere interactions. So you can start to see where we've labeled the atmosphere, and then there's the ocean. And then what scientists are truly interested in is what happens as the interaction in between. So data sets that get you to this. One of the problems with this kind of data set is that at NASA, they would usually so they would spend tons of compute time, generate the animations, and then you would just have to scrub back and forth on the animation. And our efforts have been to make this interaction, instead of just a video that you can play through, something that you can actually explore. So as I mentioned, there's three data sets totaling 4 petabytes. The first one is the diamond data set, and this consists, it's 1.8 petabytes of data, and it consists of 2 pieces, the GEOS atmospheric model and the ocean model. The atmospheric model is about 600 terabytes in size and uses a cube sphere grid. 6 faces are available for each of the fields, so this one has lots of different fields that come with it. But to get to access the data, you just access each face individually, and we provide tools that help access that as well. So when I talked about all the different fields, these are the ones that come with this atmospheric model. So things about pressure, wind, air, carbon monoxide, carbon dioxide, clouds in terms of ice, and clouds in terms of liquid water. And the data set has a timeline for about 14 months, starting from initial conditions from January 2020. We will provide stubs for that allow you to load the data that we have served, like on the seal storage, and then be able to treat it as a NumPy array, and then work with it within Jupyter Notebooks. And our contest website will have all the stubs for this. The next piece of that first data set, the diamond data set, is the ocean model. And this is 1.2 petabytes of data. Here's a visualization of just one of the fields. So each of the fields are about 200 terabytes. And this is the east-west water velocity. And this is one of our dashboards built using Jupyter Notebooks, loading the data from seal storage. The next data set is the oceanic model, and this is about a 2 to 4K grid spacing with 90 vertical levels. So every field has 90 levels from just below the sea level to 6 kilometers deep. And it's represented by 12 faces, each with a shape of 2160 by 2160, attached together on a lat-long grid with the grid structure provided in the slide. And this one, again, also has many fields. So east-west velocity, north-south velocity, vertical velocity, salinity, and temperature as all parts of the oceanic model. And this one has a timeline from January of 2020 to March of 2021. Again, where each of those fields has a depth, which is that third parameter in the shape of 0.5 meters below sea level to 6 kilometers below sea level. And again, this is just an example of what the Jupyter Notebook looks like, and it provides you with a NumPy array that you can use your visualization skills at. The next data set is the oceanic model, which is a 14-month global simulation of the ocean for September 2011 to November 2012. And this one is the goal of this data set is to capture complex ocean dynamics. The data set in total is about 2 petabytes, and each timestamp is about 30 gigs. And this one has the following fields. So sea level, sea surface, east-west velocity, north-south velocity, vertical velocity, temperature, and salinity, again at the 90 depths. And this timeline goes from 2011 to 2012. And again, we provide the slides that have the how we fetch it. This one is being fetched at Pelican. Note that we are, if you started digging into this one, we're still processing all of the fields. So not all the fields are available, but we expect them to be available within the coming months. This is the last data set, and this one's about climate projections. And this one has a lot more time features, which is kind of fun to play with, and has captured the finer climate gradients influenced by geographical features. And it's about 38 terabytes. But there are a lot of variables involved in this data set. So there's 30 different models. So again, this is simulation data with 3 different scenarios and 8 variables. And the 8 variables include things like air temperature, precipitation, relative humidity, and short and long wave radiation. Like I said, the timeline is on this one is kind of fun because it goes, it has both historical, so from 1950 to 2014, as well as future projections of 2015 to 2100. And these are on a about 25-kilometer grid. We have a link to the dashboard that we've built that processes this data. And we are currently serving this data on our side. And you can access it by setting up the different variables, or you can look at the dashboard that we've provided with this link. And again, I provide at the end the ski where all of the data is on our website. Okay, so the fun part is, okay, so now you have this massive amount of data. What do you do with it? Well, we've come up with a few tasks to help you get started on your exploration journey. So here's just kind of like a fun project of looking at the air temperature as it varied from 1950 to 2100. So load up that last data set that I just told you. And participants are encouraged to try simple visualizations to show how the air temperature changes over the time, look at humidity as it varies around the globe, and provide interactive visualization that shows how allows users to play with the data. And then task number 1, so getting to more complicated questions, looking at the GEOS data, and looking at global atmospheric wind patterns. And we provide the different variables that are important for looking at this, the name of the data set, and kind of a challenge. The second one, we start getting into bigger things and looking at the interaction between atmosphere and ocean. So here we would encourage participants to find a particular region and a particular time period. And this would be like when there was a hurricane, cyclone, monsoon, something that you can find in the data, and then try and find a way of generating some visualization and interaction around that idea. And we have a sample use case with one of our dashboards that you can, and all these slides will be up on the, and all this information will be on the website. And here's just some more things. So the different variables that you'd need to look at with the ocean data, and some more questions. And then our third task is looking at the 3D structure of ocean currents. So looking at mapping different velocities, fields, and we're encouraging participants to look at generating layered visualizations that can show how the ocean currents change with depth. And again, encouraging the variables that would be appropriate. And then we've left an open-ended task. So now that you've played with the data, hopefully you will have your own ideas of what you could do. We encourage you to work with domain scientists. We encourage domain scientists to enter their own projects. All of this will be evaluated on usability. Again, we're not looking for just canned movies, but some kind of visualization that enables users to understand and manipulate the data. Creativity and innovation. Are there novel visualization techniques that provide new insights to climate data? And scientific accuracy. Does the visualization accurately represent the underlying data and phenomenon? So we encourage submissions with any number of the tasks completed, and we will be updating our website with the judges that will be reviewing this project. I just thank our supporters for this project. And perhaps one of the most important things is at the end this afternoon, we will be giving a Viz tutorial where we will provide you hands-on access to actually playing with this data. So we will go through some Jupyter notebooks and show you how to install them and use them on your system. So if you're interested in this challenge at all, please attend the IEEE Viz 2024 tutorial 7, which starts after this session. And then here's the big QR code for that SciVis contest. If you have any questions, feel free to contact me or any of my co-authors. And that's it for me.
Thank you. That sounds super exciting.
Yeah.
And that it's a good thing people have 2 years to work on it.
It's kind of a big project. We decided that we would probably benefit from jumping in a little early.
I suspect people spend the first year just getting to know the data.
Well, if you come to the tutorial, it may be faster.
Cool, cool. All righty. I believe that is just about everything. All right, so just for the SciVis 2024 presentation, for the best paper winner, you will hear from probably directly from Teresa Marie Ryan, possibly from Tim or I. Certainly you can reach out to Tim. And thank you. Thank very much to both teams for coming and presenting, and thank you for everyone for putting up with our unfortunately fully virtual contest this year. And I look forward to seeing everyone in Vienna next year. And thank you to everyone. And I think that's everything.
Thank you, Karen. Thank you for your organization. Thanks.
Yeah, thanks.
Thank you.